Alexandra draws a letter A, which stands on the x-axis. The left side of the letter A lies along the line with the equation y is 3x plus 6. What is the x-intercept of the line with the equation y is equal to 3x plus 6? Well, to get the x-intercept, you set y equal to 0, so then 0 would be equal to 3x plus 6, and therefore x would be minus 2. So I guess the point is minus 2, 0. The right side of the letter A lies along the line L2, and the letter is symmetric about the y-axis. What is the equation of L2? Well, as always, every line is of the form y is equal to mx plus b. And then to get m, which is the slope, we would, I guess, do rise over run. And we can do rise over run. This point, of course, is going to be 0, 6. Yeah. And then we figured out that this was minus 2, 0. And since it's symmetric, this point would be 2, 0. So those are the points I'm using, just in case you're wondering where did I get that from. So this is minus 3, and therefore y would be equal to minus 3x plus b. Substitute either of those points. I'll just substitute in the 0, 6. And that means b is 6. And therefore, finally, the equation of that line is y is minus 3x plus 6. Determine the area of the triangle formed by the x-axis and the left and right sides of A. Okay, so area of a triangle is 1/2 base times height. And the base is from here to here, so that looks to me like 4. And the height is from there to there, and that's 6. So that would calculate to 12. Alexandra completes the letter A by adding to figure 1. She draws the horizontal part of the letter A along with the line y equals c, as in figure 2. The area of the shaded region inside the letter A and above the line with the equation y equals c is 4/9 of the total area of the region above the x-axis and between the left and right sides. Determine the value of c. So let's see here. What's the strategy? 4/9. So this shaded area is 4/9 of the total area. And the total area we just figured out was 12, correct? Okay, so we've got 4/9 of 12 is the shaded area, and that is 16 over 3. So 16 over 3 is 1/2 base times height. Base times height. All right, now I have to figure out what is the base and the height, and obviously that's going to involve the letter C. So the equation of that line, this line here, that line, is y is equal to minus 3x plus 6, right? We figured that out earlier. So what I am interested in is what is the x value when y is c. So when y is c, what is going to be my x value? And when you solve for x here, you'll get x is equal to 6 minus c over 3. So that basically is the x value when y is c. So I guess this point right here, that point. Okay, so that's part of it, I think. So the base would therefore be double that, since we have to multiply it by 2. So it would be 2 times this guy. So 12 minus 2c over 3. And then the height, I think that's pretty easy, because this is 6, and that's c. So the height just from there to there would be 6 minus c. And I think that's it. That will allow me to calculate for c, which is what they want. Okay, so let's do this here. So it'll be, let's multiply through by 6. So 6 times 16 over 3, and that gets rid of the fraction, and that just leaves me with this 12 minus 2c and 6 minus c. And then I can factor out a 2, and I'll get 6 minus c. And this is 6 divided by 3 is 2. 2 times 32. 32 divided by 2 is 16. Oh, sorry, hold on. I gotta keep that 32 in first, and then I can write that 16. And then that's 6 minus c squared. And then if I take the square root, I get 4 is 6 minus c, and therefore c would be 2. And that solves the question. Determine the positive integer x for which 1 over 4 minus 1 over x is equal to 6. 1 over 4 minus 1 over x is equal to 1 over 6. And if we multiply it through a common denominator, that whole big long song and dance, we will get 20. Well, actually, first of all, before I do that, let me just tendency to do things a little too quickly here. Let me just put it over that, and then we can do it. So it'll be 6 minus 4 over 24, 1 over x. And that looks like 2 over 24 is 1 over x. So that's 1 over 12. And therefore, x is 12. Part B. Determine the positive integers ab for which ab minus b plus a minus 1 is 4. Okay, so let's see here. So we've got ab minus b plus a minus 1 is 4. So factor out a b, then we get a minus 1. And this is already a minus 1, so that is very helpful. Factor out the a minus 1, we get b plus 1. So we have a sort of a limited choice. We've got basically two numbers. They're both positive integers. Two numbers that multiply together to give 4. So a minus 1 and b plus 1. There's limited choices here. You could have 4 and 1. You could have 2 and 2. Or you could have 1 and 4. And that, I think that's it. And then we've got to figure out a and b. If a minus 1 is 4, then a is 5. If b plus 1 is 1, then b is 0. And then similarly, this would be 3 and 1. This would be 2 and 3. But keep in mind that a and b are both positive integers. So this guy here can't be used because b is 0 and 0 is not a positive integer. So the only ones that can work are these guys. So I guess my pairs are 3, 1 and 2, 3. Determine the number of pairs of positive integers for which 1 over y minus 1 over z is 1 over 12. 1 over y minus 1 over z is 1 over 12. So same kind of story here. You have to kind of fiddle around with this. And let's see here. So we got 12z minus 12y is yz. Let's put everything on one side. yz plus 12y minus 12z. And factor out the y. Z plus 12 minus 12z. And then we have to use a little bit of fancy algebra here. Minus 144 from each side to help factor this a little bit better. Minus 144. And what that does is allow me to factor out at minus 12 and then z plus 12. There we go. And that hopefully will help us. So we have z plus 12 and then y minus 12. Okay. And then you guys from the previous one can kind of see where we're going to go with this. You got same kind of story here. Let's make a little table. And let's see what we get. So we've got z plus 12, and then we have y minus 12. And they both multiply to give minus 144. So we have some limited choices here. Hold on, let me think about this. So we have 144 and negative 1, 72 and negative 2, 48 and negative 3, 36 and minus 4, 24 and minus 6, 18 and minus 8, and 6 and minus 9. Now, there is a very important point here that we must, from the actual basic equation, since 1 over y minus 1 over z is a positive, that basically means that z is greater than y. That's very important here. Z, let me put that over here actually. Z is greater than y. Yeah. And that what that does is it kind of limits our possibilities, which is good. Otherwise, we'd have to keep going. Okay, so now all we have to do is figure out what is the value for z and what is the value for y. So z and y. So same thing, right? If z plus 12 is 144, that means z is 132, and if y minus 12 is -1, then y is 11, and so on. So you just fill these in. 36 and 9, 24 and 8, 12 and 6, 6 and 4, and finally 1 and... hold on. Let me see if I'm doing this right. And I think that is the complete table filled out correctly. So therefore, we've got 7 pairs, and those are the 7 pairs, 1, 2, 3, 4, 5, 6, 7 of y and z. And finally, prove that for every prime number p, there are at least 2 pairs Rs of positive integers, for which 1 over r minus 1 over s is 1 over p squared. So same thing. We first have to do this fraction. P is a prime, right? P is prime. Okay. So when you do this, you get p squared s minus p squared r is equal to rs. Put everything on one side, and we get rs plus p squared r minus p squared s, and then rs plus p squared minus p squared s, and minus p to the power of 4 rs plus p squared and p squared s. Very similar to the previous one, it's just we have letters this time instead of numbers, so it might be a little bit abstract, but it's not so bad. S plus p squared, factor out a p squared, I think, and s plus p squared, and there we go. We have a very nice s plus p squared and r minus p squared. So that pretty much completes the factoring. And then now, same thing as before. I think by now you're getting to be an expert here of how to create this table, how to fill it out. So we got 2 numbers, and then this time they multiply together to give minus p to the power of 4. And so we got r minus p squared, that's the first factor, and s plus p squared, and then r and s. Now, s and p, they were positive integers. Okay, yeah, that's important. So if s and p are positive integers, then this guy is greater than 0. Yeah, this one I'm not sure what it'll be, but that one is for sure greater than 0. Okay, well, I think we just have to find at least 2. At least 2. And if we do that, then we've proven it. Okay, that shouldn't be hard. So 1 and 2. I don't even think I need to go to number 3 here. So if I can find at least 2, then I proved it. Okay. Let me think about this. Did they give us anything about R and P? Like in terms of their values? Oh, just like the last time. Sorry, I got a little excited there. Pretty much the same as last time. Because of this, I got it. So because of that, we know that S and R, now very similar to here, you remember? We made that conclusion that, where was it? Z is greater than Y. So we can make the conclusion here that S is greater than R. Yeah. I hope that's true. I don't think it really matters, but well, I just wanted to put that in there. I think it in some ways it might help us, because if you kind of further discuss that type of issue, 1 over r minus something is equal to 1 over p. So that means 1 over r has got to be greater than 1 over p squared. And then by that philosophy or inequality, r has to be less than p squared. Yeah. So that's actually very helpful, because we are told that r and p are positive integers. So r because it's a positive integer, it's got to be at least 1. And I've just deduced that it's less than p squared. So that's helpful actually, because then r minus p squared would be less than 0. So we can put all that stuff in here. This is less than 0. And yeah, I think that will help us. So our only goal really is to get 2 examples, and I think we can do that. So let's say, since this guy is less than 0 and it's an integer, let's just say let's just give a value here, negative 1, because it's got to be less than 0. And if that's the case, then that means this guy is negative 1. That means this guy has to be p to the power 4 in order for that equation to work. And then you just solve for r. And when you solve for r, you'll get p squared minus 1. And when you solve for s, you'll get p squared minus p to the power 4 minus p squared. And similarly, you can do that for other numbers. Just off the top of my head, for example, if you made this p to the power 3, this guy, and this guy minus p, so that kind of thing, then this would be p squared minus p, then this is p to the third minus p squared. And that's it. I've got 2 examples that show that we have 2 pairs that satisfy that equation. And I think that's all they're really getting at, and I think everybody's answer might be slightly different as long as you get 2 examples of 2 positive integers. A string of length n is a sequence of n characters from a specified set. For example, BCAAB is a string of length 5 with characters from the set ABC. A substring of a given string is a string of characters that occur consecutively and in order in the given string. For example, the string CA is a substring of BCAAB, but BA is not a substring of BCAAB. List all strings of length 4 with characters from the set ABC in which both the strings AB and BA occur as substrings. So we want both AB and BA to occur, and these can be combined as ABA. So basically ABA's got to be in all of my 4 character strings. Okay, so we just have to manually list them. I don't think there's any other way. There's that one. There's that one. So this is just, a tedious exercise of just trying to list strings. And I think that's it. But that's just half of it, I think, because then you can also do BA and AB, but you can combine them like BAB like that. And then that would give me another 6, I believe. And I think there's going to be at least a couple doubles. Let me just write these out first. B, BAB, and C, BAB. Okay, so these guys, hold on one second. There's a few that actually don't sort of fit the mold of this or this. There's this guy, and then there's also the one like this. So these both would have an AB and a BA. Yeah. So I guess we have all of these guys. So that's what, 14. So there's 14 in total. But I think there's going to be at least a couple doubles here. Let me see if I can identify the doubles, because those can't be counted twice. Let's see here. This one, that's a double. You notice that? Baba. And then there's going to be at least one more. This one, ABAB. That's twice. So those we have to subtract from the 14, and then it gives a final of 12. So that is that. Now the last one, determine the number of strings of length 7 with characters from the set ABC in which CC occurs as a substring. Well, we have 7. 1, 2, 3, 4, 5, 6, 7, right? So if we just look at the total, there's 3 possible letters choices for each. So the total would be 3 to the power of 7, which is 2187. Now that's the total. Now they want only the ones that have CC as a substring. But I think the quickest way is to find out the number of strings that do not have the CC. And then we can subtract whatever that number is. Let's say it's X. We can subtract that from 2187, and that would give me my actual answer, which is the number of strings with CC. All right, so here we go, and I think there's going to be a few scenarios. The first is if you have no CCs at all. No C's, sorry. No C in the string. So all 7 letters are either A or B because you're choosing it from A, B, C. So that basically means that each of these spots has 2 possibilities, either an A or a B, and the total would be 2 to the power of 7, which is 128. So let's save that guy. That's going to be counted later on. Okay, the next is when you have just one C, and that means that for these 7 spots, you're going to choose one of them to be the C. So from 7, choose one. And for the remaining 6, each of them will have 2 possible choices. And when you do that math, it's 7 times 2 to the power of 6, which is 448. So we'll save that one. Now the next one is when you have 2 C's, but those 2 C's cannot be together, right? Because we're trying to figure out the number of strings that do not have the CC. So, okay. So we got 1, 2, 3, 4, 5, 6, 7. Yeah. And there's 15 ways to put the 2 C's, C and C, so that they are non-adjacent, meaning they're not side by side. And I will tell you to list them. That's your homework, not mine. And then the remaining 5 would just have 2 possibilities each. So that will be 2 to the power of 5 times 15, and that's 480. And then finally, we have all 3 letters are C's, but none of them can be adjacent. So I think there's a very limited way of doing that. Let me just see here. How do you do that? There's 10. There's 10 ways to do that. To put 3 C's non-adjacent. And again, you list them. And it would be therefore 10 times. And then we have how many? 4 spots left, and each of them has 2 choices, so 2 to the power of 4. And that's 160. And then finally, we have, let's just put it in the side here. The final scenario is when you have 4 C's. And 1, 2, 3, 4, 5, 6, 7. The only way to put 4 C's non-adjacent is that. So there's only one way. And the remaining 3 will have 2 spots, 2 choices each. So 2 to the power of 3, and it's 8. And that's it. I believe that's it. So we got this 128 plus the 448 plus the 480 plus the 160 plus the 8. And that totals 963. Oh wait, that totals 1224, and then we have to come back here, and from 2187 subtract that 1224, and that gives me my 963, which is the answer to the question.